All right. And we are live. Good morning, good afternoon, good evening. Ali, you're in New York.
Yes, I am.
All right. How's the weather in New York? We got to talk about the weather every time.
I mean, it's not bad today, actually. You start to feel that spring is finally here.
Yeah.
Though, that being said, this winter was not bad in particular. So the global warming is here. So
Yeah.
we all felt that in at this part of the world.
Yeah. Yeah. Well, I mean, it's a beautiful day here in London, Ontario, Canada. I got my Canadian coffee, my Tim Hortons, shout out. And we're going to have people in, it looks like from all across the world. We got some West Coasters. Hope you guys are staying dry over there. We got some people in Europe. I hope everything is good this evening over there. So let's just dive right in. We got quite a lot to go over, and I think we'll have some time afterwards to maybe ask some questions. If anyone has any questions as well during the live stream, pop it into the comments section, and I'll get it up on the screen here, and we'll talk about it if it's relevant to that portion of the presentation. But yeah, let's get started if that's okay with you, Ali.
Absolutely.
Awesome. So I think most people know me from my LinkedIn, and obviously you're watching this through my LinkedIn, but some people may not know Dr. Ali Khaloo. So, Ali, we were introduced not too long ago, and we've been working quite closely ever since. Do you want to give us a quick little brief on your background and how you got started?
Absolutely, with pleasures. So as Ted mentioned, I'm Ali Khaloo. Looking at my background, so I did all my education in civil engineering. Worked as a civil engineer. I did bridge inspections and building inspections, designing new buildings and bridges as well. And basically, at some point in my career, I was like, the status quo, has to, get changed, and you should do that from inside out, given how old school is this whole industry is. So as I was doing my research in academia, I got more and more into machine learning and AI, and basically how you can monitor the assets at scale. And
Hmm.
basically, at any point in time, you both have the macro view, a good macro view, and very granular information of each and every asset that you have in your portfolio.
Hmm.
That's how we did our research, and we did that R&D, and developed our patents, if you will, and wind up starting the company, or basically commercializing all of that in 2019. So we are a
Yeah.
startup out of Cornell University,
Right on.
and we have raised a good few $1 million from institutional investors, and we are working with clients in all parts of the world at this point.
Awesome. Yeah. No, well, I mean, this is a problem that exists all around the world. So boundaries don't really change. A bridge is a bridge, a road is a road, et cetera. Right. So
Yep.
when did you start getting involved with machine learning and trying to tackle this problem? How long ago was that?
It was 2013. So it
Oh, wow.
was even before the hype of deep learning, neural network, and all that kind of, like, deep neural networks, I should say.
Yeah.
So it was like I started with the little bit old school machine learning, which you had to engineer all the features that your machine learns, and basically that whole route. And then more relevant to what we are going to talk today, on the 3D reconstruction and the whole thing, like starting in 2014, we started to work on all of them.
Yeah.
Back then, there was not many um, drone companies or commercial drones out there. I mean, this was
Hmm.
still before FAA
Yeah.
regulation 107, of course, I'm talking about.
Hmm.
So we actually had to design our own drones and design our own robots, and put, like, being able to carry different payloads. And we did one of the very first bridge inspection with a drone in 2015, and believe it or not, we had to fly to Alaska to do it. So that
Wow.
was the only place that they let us to conduct this kind of drone-based survey, if you will. So
Yeah.
I've
Well,
been
I
doing this
mean,
for a good amount of time at this point.
it's still, we're moving ahead quite a lot recently, but there's still a few things like that are getting in our way. But I'm sure that that's going to change very quickly. In terms of AI, we're full steam ahead on AI. Like, what a week! We had ChatGPT 4. We had all of these other companies releasing their latest products, and so we're right on the hype train right now.
Yeah.
We're going to be talking a little bit of a different type of AI, right? Like in our field, chatbots and chatting is very could be helpful, but we're kind of in the computer vision field, right? Trying to make computers understand images and pictures like we humans can interpret them. So in the webinar today, we're going to talk mostly about that, but I just want to get started in like how AI is kind of making its way throughout the three different components of what we do in the data collection, the reconstruction, and data analysis in this field. And when I say this field, I'm a drone service provider, so I kind of have to touch all three of these, and I see all of them being affected in one way or another and enhanced by AI, and I'm really excited about that. So let's just quickly overview 3D reconstruction, right? What I mean by that is surface from motion, photogrammetry generally, taking 2D data images and converting it into a scale constrained mesh. And I think we're seeing a lot of advancements in AI there, specifically with nerfs. This is looking really promising to me. Here's an example that I did with a tail section of a Hawker business jet. I teach at an aviation school, so I have some access in this hangar, and I decided to collect this data with the SkyDeploy inside, and I ran it through photogrammetry pipelines, and this is what I get. And then I tried running it through a brand new app you can find on the App Store. It's called Luma AI, and they use NERF technology or neural radiance fields to compute the reconstruction. And then they also give you the mesh, which is really unique in the Nerf world. But you can see right away that the holes, the Swiss cheese on that tail section, has been patched up, and it looks pretty geometrically correct, right? So this is a huge advancement. We have a lot of problems in reconstructing shiny or very flat materials in terms of their surface texture. So I think this is really important, especially in the field of inspections for civil engineering, because we're running across metal surfaces all the time. That's 3D reconstruction. So we have some work to do there, but we're on our way. With data collection, that's one of the biggest factors in really moving this forward, I think, because there has to be you have to really understand there's two different methods of collecting data: fully manual, but then there's automatic, of course, which is what we've had up until now. But automatic is still difficult. You can automate, but it's still dependent on many factors. It takes a lot of planning, a lot of skill in the field and before to do that planning and make sure that everything is safe. In a lot of cases, you're dependent on other factors like GPS, which is completely out of your control. And I'm personally seeing a huge move forward in this field and making this more scalable, easy to use, using drones in areas where you would never have put a drone before, like under a bridge. And this has me really excited because this means it's scalable. And as a business owner, I always think about scale. I always think about how are we going to be able to grow and do everything everywhere all at once. Movie reference there. And this is this is my favorite component of the data collection part is the AI in the flying of the aircraft. Specifically, the example you're seeing here is the SkyDeploy S2 Plus with 3D scan that I used for this facade inspection, and I planned it with an automatic drone in mind first. Then I tried 3D scan when I got there, and it just worked, and it was so easy, and I could hand it to any one of my employees, and then they're off and running. And then finally, data analysis. That's what we're going to be talking about in depth today. And data analysis, I mean, this has been around forever. We're always analyzing some sort of data. But in the civil engineering world, it gets pretty complex. And even with drones, that complexity remains, right? So Ali, you shared with me the slides on the left
Yeah,
here. Can you walk me through what we're looking at?
absolutely, absolutely. So before jumping, all in on AI and analyzing visual data, let's take a step back and understand what is the status quo. And as I mentioned before, I've done it myself, so I have first-hand experience on this one. So when you're looking at the way that you're creating data from our assets and the whole basically condition assessment inspection, which later on you're gonna use that data for decision making. That whole pipeline, it's very much precarious and outdated. And when you're looking at the details of it, it really didn't change much since the 70s. So what happens right now is you have very skilled engineers that you have to send out there, and now they have to literally climb and walk miles and miles of infrastructure, let's say bridges, and with nothing better than their naked eyes, they have to look for millimetric damages, such as cracks. Sometimes it's like literally naked eyes. Sometimes it's hammer sounding that they have to do to find the hollow area. Sometimes they have to use binoculars to look for different things. And after doing all of that, which by its nature is going to be inconsistent and subjective, you
Mhm.
have a newbie going out or you have a very experienced inspector, you're going to get different results. And that's known within the industry. After you're doing that, now you're coming back to your office and you have to put together a report. So in the middle, what you're seeing are actual reports from a building facade on the top and on the bottom from a bridge. That in these cases, basically now you have to go through your field notes, go through the images, which like the ones that you're seeing here, by nature they are decontextualized. So you don't know exactly from where you took those images unless you're making like clear notes and all of that. And now you have to put together those reports. And in some cases, or in a good number of cases, you have to go in AutoCAD and start drawing that facade, that element of the bridge, and you have to draw the damages, which has the one that you're seeing on the in the middle on the bottom. Those red lines are cracks that drew by an engineer manually
Mhm.
on that asset.
Mhm.
So it's a very tedious task to do it. And when you're looking at how you're saving that information, and keep track of our assets. So it's nothing better than Excel sheets. So
Yeah.
piles and piles of Excel sheets that you have in in these data management solutions that you have out there, which it's good. They're in existence,
Yeah.
but are they efficient? Are they up to the standards of the 21st century? I don't think
Mhm.
so.
Yeah, well, I mean, it looks like they're running on Windows 95, and I wouldn't be surprised if that's like a screenshot taken yesterday from one of those offices somewhere. And so
Yep,
it's a lot of information that we're trying to boil down to a few 2D reference images and a fancy database, but it's really just an Excel spreadsheet at the end of
absolutely.
the day,
And,
right?
and keep in mind, this is the way that we keep track of our assets, and
Yeah.
all of this information feeds our decision making processes,
Hmm.
which is basically okay. Now I have billions of dollars or trillions of dollars,
Hmm.
and now I want to invest on my whole portfolio that I manage. Let's call it like the 614,000 bridges that you have in the states, or any type of infrastructure. That inconsistent and subjective data goes into that decision making, and no wonder we are not optimized when it comes down to the spending that we are doing,
Hmm.
or we are not basically on top of our infrastructure in the sense that to do, as everybody likes to do, proactive asset management. That
Yeah.
is not there because first things first, we don't have the good data in place to make decisions off it. So that's
Yeah.
important to understand.
Absolutely. So you're in the thick of it. You were the one doing some of this work and making these spreadsheets and these drawings. And I
Yep,
guess that's where the inception, the idea for RN came from, right? And that's the problem you wanted to solve. So that's what RN is about. It's about ingesting various types of data and then using AI, computer vision, a whole mixture of technologies to really streamline that final process and then essentially make better decisions because everything is in one place, but it's also been really boiled down to what matters and efficient.
absolutely.
Right.
Absolutely. So you have to keep in mind that we are capturing a lot of data from these assets,
Mm-hmm.
and different sources. Sometimes it's something as simple as photos from a point and shoot camera or your cell phone. Maybe you get more sophisticated and you add a drone to the whole data collection. Maybe you have lidar.
Sure.
Maybe you have 360-degree camera. Maybe you have infrared. So what we do at our company is, and what our product does is, it takes that data from our clients, then it's run its magic,
Hmm.
and then as an output, what you get is a highly detailed visualization of the asset
Hmm.
and its health through time, as well as preventive maintenance plans and capital allocation plans.
Hmm.
But when
Hmm.
we're talking about the 3D models and the way that we are doing this change in time analysis, it's based on the information that you're seeing on the right hand side. So
Yeah.
basically, we are creating 3D models. So all the analysis happens in 3D. So we are detecting all the damages, we're quantifying those damages, we're providing the severity analysis of them, and all of them is based on the codes that we have in each country. Let's say in
Right.
the US, you do that for bridges, you do that based on AASHTO element level bridge inspection manual. So
Hmm.
everything is according to the standards, and it's basically part of the workflow of how we do the inspections, but now it's augmented through technology and through AI in particular.
Yeah, yeah, and okay, I'm never gonna say that 3D is the only way to do things. It's one of the ways to do things. It really depends on the data and the structure and what you're doing, right? If it's a flat road, maybe 3D is not necessary in absolutely every way, but you support basically everything. So
Yes.
its completeness in the input, and then the inputs also have to be good. Like you can't, there's no magic here. Like if you can't see the damage in the images or the data, you're not going to be able to pull that out of thin air. But
Absolutely.
when those things come together, and as they are getting easier and easier and more scalable to put together,
Hmm.
then you get the 3D reconstruction, the 3D model from photogrammetry inside of
Hmm.
your product built in. You don't have to do that elsewhere and bring it in. You get the analysis through the AI, so that speeds up an insane amount of time in terms of going through and looking for it. Right, that's 90% of the work, and then an engineer can validate it afterwards. And then you also get, my favorite part is the quantifiable data on a damage by damage, element by element level, and that's
Absolutely.
something that before I saw AREN, I hadn't seen before done completely in an automated fashion. And that got me really excited. So we had a lot of questions with some posts I put up. So we decided to do this webinar to kind of get people into understanding what is required for this to work well, and then how it works, because AI has to be explainable for it to be really adoptable. Um,
Absolutely.
but I think this really shines when it's done over time, right? You take a look at a bridge 1 year, then maybe 2 years later, you do the same analysis and you get these assessments. And these assessments show you the trend just based on the quantity of findings. And so this is a slide that I put together to kind of explain what I mean, but you saw this as well. Does this make sense from an engineer's perspective, from capital planning?
So, short answer, absolutely yes. And you have to keep in mind that the whole goal of the asset management, and let's say you're an owner and you're going to have that asset for the next 50 or 100 years. These assets, they usually outlive us.
Mm,
What happens here is you want to minimize the life cycle cost,
mm,
and then at the same time improve the serviceability of that asset. So those are the top two things that you want to do.
right.
And in order to do that, what we're as we mentioned a little bit earlier, you need to have good data. You need to have robust data and assessment. So
Mm,
what's happening here is, as you do these kind of assessments over time, which that's you know that's by law, you have to do that at a
mm,
certain frequency. You have to
yep.
go back to your asset and do it. Now what we are able to do is, because you have this detailed information, now we are able to do this assessment over and over time and do this change analysis, so
Hmm.
we can back to what you mentioned, Ted, that quantification, it's absolutely important,
Yeah.
because now with that quantification you can say, okay, I had, for example, 1000 cracks before, now I have 2000, so I have more cracks.
Yep.
On top of that, the cracks that I had in last time, 2 years ago, 6 months ago, whatever that is, now you can say, okay, what's the trend that I see? And
Hmm.
that trend is going to be per damage, so you can see
Right.
each of them are growing by 25% in terms of length and 50% in terms of width. And at what, back to the 3D, the 3D helps you to contextualize everything. So it's not like,
Hmm.
oh, I'm looking at this one photo, God knows where that photo is coming from. No, you know exactly where on your bridge or on your dam or on your building facade you are.
Yeah.
And that's how you are monitoring these changes over time.
Yeah, yeah. And in terms of damages in this field, there is a wide variety of findings you're after, right? And we have such a spectrum of surfaces, materials, angles, lighting. It's crazy, right? So to build an AI algorithm, right? Whatever AI kind of covers everything, but to build anything that does this automatically, you need to train it first, right? So
Yeah.
that's the first challenge is training something that is reliable and consistent. And a lot of the AI that has had a lot of success, well, if you look into it, the data that it's been trained on is generally pretty straightforward and pretty uniform across the board. It's very well labeled, right? The data sets are massive. They've been curated over a long period of time. The imagery doesn't really change. An X-ray from today is very similar in look to an X-ray from 1950. So you have this vast history and library of data to sample from. to
Mhm.
build the training data and then to eventually train your model. But in our field, it's extremely variable, right? Anyone that's flown a drone understands this. You have to be very careful, even with your camera settings, to have things look, even in the same place, look the same between different days.
So there, so absolutely. So there are a couple of things here to understand. So one is that variability that you just mentioned. So for example, with X-ray on the left-hand side that you're seeing, are there any like slight variations between them? Yes, but in general, they're very much controlled. They're like from
Hmm.
the same part of the body, and that's what you do for each patient and whatnot.
Hmm.
In our world, that's not the case. I mean, even concrete as an example, which is
Hmm.
the most used material on Earth, it can look differently. It can look different in different countries, and the pre-stressed versus reinforced concrete. So it's
Yeah.
some of them are a little bit yellowish color, some of them more grayish color. Like it's all over the place.
Yeah.
And on top of that, as you mentioned, let's say X-rays, let's say like medical imaging as a whole, you have been doing that for a good amount of years. But guess how many years we have been collecting image data from civil infrastructure assets? Not
Yeah, I
that
mean,
much. I mean,
couldn't even
drones
fly a
really help.
drone. Couldn't even fly a drone in 2014, right? Like, yeah, so at
Yeah,
least
absolutely.
after that.
Absolutely. Absolutely. So that's one. The other piece is with the training data. So we're talking about supervised learning. So you
Right.
need data in order to label and then train your model.
Hmm.
When you're looking at some of the other fields, which are, they're hot
Hmm.
these days, like autonomous vehicles. So you
Hmm.
have major companies that they spend a
Yeah.
fortune
Yeah.
to create data and label them. And those data, in particular in this case, it's from the city. So it's a dash cam that you put there, and you easily can drive through the city, and then you have somebody who labels it.
Sure.
And
Sure.
it's sort of, you have this vast labeled training data available that both the companies and the people in academia are using them to develop new algorithms. Again, that piece, that standard training data set, it's
Hmm.
not there for civil engineering.
Yeah.
You
It's
have
just.
very, very limited, and it's only maybe just one material, one particular damage. And even in those cases, it's like super close up images.
Yeah.
And in reality, that's not the way that you capture the images from your asset. So
Right.
training data and having that and having good amount of that, it's tough.
Yeah.
And we have been busy for a good amount few years just to do that.
Trying to work on that problem. Yeah, no, it's a big problem. And like you said, the data isn't collected with the intention of making it into 3D geospatial formats after, right? So no photogrammetry intended with the data collection, even if the data set exists.
Yeah.
So that's a big problem. Now, once let's say you have a data set, you've trained it. What kind of scene understanding is there, and sort of what do you need to apply in the case of engineering and civil assets?
So that's a very, very important thing. Like it's not just, hey, let's apply AI. Let's
Mm,
apply AI to this very, particular problem. So let's start with like how the computer sees things and identify things and how that evolved over time. So on the left hand side of your screen, you have the image classification. So what it does is you give the image to the computer, to the machine, and through AI, it tells you what it is in the scene. So it gives you the what answer.
mhm.
In this case, bottle, cup, cube.
Right.
But then it doesn't provide you with the very important information, which is where that object is or where that region of interest is, which is maybe damages in the case of engineering.
Right.
There it comes into play, the one in the middle, object localization. So now okay, I have cup, cube, bottle, and now
Mhm.
you know the exact locations of them.
Yeah. Well, you know the exact location on the image, but you don't know the exact location in space, right? So
Absolutely.
you have coordinates, but there's just X and Y coordinates on this image system, and four of them make up a square. So it's there, but it's not really there, anyways, right?
Yeah, absolutely. And when you're looking at only images, especially if you've captured the images for the purpose of 3D modeling,
Mm,
you're going to have images with a very high overlap, 50, 60, 70% overlap.
yeah.
So let's say that bottle that you see there, you very high chance that you see it in 5 different images.
Yeah.
And now you're going to have identification of bottle in 5 different images, and
Hmm.
basically you're going to say, hey, I found 5 bottles, but in
Hmm.
fact that's just one bottle that you see in different images. So that's why for us it was very important to do everything in 3D, so it's just one piece of asset that you're working on. But essentially, the issue with that object localization, the one in the middle, is yes, it gives you the what and where,
Hmm.
but doesn't give you the geometry.
Hmm.
Let's say, damages. You need to know what's the width of your crack. You need to know what's the depth of your spalling. There it comes the next one, which is the semantic segmentation.
Hmm.
So in the semantic segmentation, what you do is you get the where, you get the what. So basically, you do per pixel classification. And now I like the example of the cup in the middle, that you can see the handle of the cup as well. So
Yeah.
you see all the you can see the corners of the cubes.
Yeah.
So now in this way, you know what you see there, you know where they are. On top
Hmm.
of that, you know the shape of them. And
Yeah.
that is what's important when you're looking at it from the perspective of civil engineering.
Yeah, absolutely. Civil engineering, there's no engineer that's not going to tell you that scale is important, that location in spatial context is important. Of course, everything like that is super duper important more than anything. And it's critical, right? These are assets that are supporting our lives. It literally, when we're on them, when we're driving through them, and without them, our economy would fail. So the semantic segmentation, for people to understand the level of sort of understanding of where things are, we're still in the image coordinate system, right? The X and the Y, but we're basically assigning every pixel to a group. So the blue is the bottle, the purple is the cubes. Through this, we have we still don't have real scale. We can't associate it with color, or sorry, with distances in the real world. But because we're doing photogrammetry, that will take care of that problem because we're collecting the data with that in mind. So the training data needs to be labeled and ready to go at a high quality in this format. And here's an example. You shared these from some of your data internally. And so, what are we looking at? What's with all the colors?
Absolutely. So, as we mentioned, with semantic segmentation, you do per pixel classification. So what we're seeing here is some of the annotated images. Let's
Mm,
say, so everything which is red, it's the background. So it's the part that, let's say, you don't care.
yeah.
But you have different colors, and each color shows different damage. So the yellows are showing the cracks. The blue one are showing the holes, the pink one is showing the spalling, and the green one is showing the fluorescence. So
Mhm,
as we discussed, that training data is unavailable. So internally, we had to put together, at this point, in we're in millions of data annotated. So we had
mhm,
to curate that data set. We had to internally label them per pixel
yeah.
for different materials. So we have done that for concrete, we have done that for steel, we have done that for masonry, and this is, you need an engineer who understands all these damages to go ahead and label that. So it was a pretty
Yeah,
remarkable task that we took.
it's time consuming, it's expensive, but it's absolutely necessary and needs to be of a high quality as well, or else you're going to
Absolutely.
have problems. So you can do so much, right? So there's other methods to improve that. And just like really quickly, image augmentations is something that I've come across and heard the term. How do
Yep.
you guys use them? Is what are we looking at here?
So, in order to create the most robust algorithm, one thing is the training data itself. That through this augmentation, basically, you took the image on the left hand side
Yeah.
and you create different variations of it, and you make it going from RGB to grayscale. You're adding salt and pepper, noise, Gaussian, so all those like filters and
Yeah.
scaling and cropping. You do all of that in order to, let's say, go from 1 million images to 20 million images. So now
Hmm.
your model is going to see more. And on top of that, you're helping with the robustness of your algorithm,
Hmm.
because now you're keep changing it and making it more extreme. Like,
Yeah.
you wind up, from the clients, you're going to have different quality of data coming in. So you have to make sure that your model have seen all of that in the first hand, so it can do a high quality analysis moving forward.
Yeah, so this was collected. This is from our runway example that we're going to show later, and this was collected on like a perfect day. But let's say that you're doing this over time. Not every day is going to line up like that, and you're not going to be able. You get a lot of things that are again out of your control. Your camera might change, the lens optics might change, so you got to account for this. And this
Yeah.
is a synthetic way of accounting for it, and all those annotations you already made are already there, so you don't have to
Yeah.
duplicate that effort.
And on
Great.
top of that, the illumination going to change. I mean,
Yeah.
if it's like 7 a.m. in the morning
Yep.
or 2 p.m. or it's like 5 p.m.,
Yep.
that same surface, it's going to look different.
shadows, overcast, right? It could change.
all of that.
And this is all being done so that we can ensure accuracy, right? Because again, these are critical pieces of infrastructure.
Yep.
And so what this shows, I guess, the way I understand it, this is your ground truth. So this is the picture with that crack in it, and then this is what our AI model has predicted. An outline of it. And there's definitely areas here where you see where they don't line up, right? So there's no crack in this section, but our AI model has predicted there to be. So we call those false positives. So that's what FP stands for. TP is true positive, and then TN is a true negative, right? So something that actually isn't there and it's predicted correctly in that pixel. And think of this as the pixels on an image, right? Your grid of RGB values. So what is this section over here? What is this referring to?
So basically, the goal here is to create the most accurate model. So
Right.
you're using different metrics to evaluate your model.
Mm,
Basically, you're running it as we call it, on a test set to see
mhm,
how good your model is. So the goal that you have is to make that as good as it gets. And the
mhm,
metric that you use for semantic segmentation is something called intersection over union. What
mhm,
it does, simple terms, so the true positives, the parts of the image that in fact there's a damage,
mhm.
it's actually over everything that you classified, and some of them are wrong, like false positives or false negatives. So that gives you an accuracy metric,
Yeah.
and that is the way that you're testing your model. So again, as you mentioned, these are high stake decisions, especially when you're dealing with damages on a piece of infrastructure that it carries a lot of people on a daily basis.
Mhm,
The last thing you want to have is having false negatives. Like
mhm.
that's dangerous. That means there's a crack there. Your model didn't pick that up.
Yeah.
So that's like all of that you have to keep in mind as you're developing this technology, and that is why we really emphasize on the training set and like how we're augmenting and how we're like pushing the boundaries in order to get to the best accuracy possible. So basically, as we're augmenting the process, we are helping the engineers to make the best
Yeah.
decision from the best data available to them.
And it's a real reputation burner if you get it wrong, right?
Yep.
This isn't you got to be ready for game time when you're going out and doing this type of inspection, and it's something that the engineers are looking at. So there's no chance for mistakes. You really have to really prepare and be ready and have great accuracy out of your models.
Yep.
So another little factor of difficulty, just really quickly, is the way I understand this slide is the crack in this image takes up such a small percentage of the pixels, right? It's just such a minute detail. To us, to humans, it's obvious, but to a computer that only sees numbers and pixels, that can really throw it off as well, right? Is that what we're looking at here?
Absolutely. So you're talking about challenges on why this is a tough cookie. This is a tough task to
Tough
take.
cookie.
So
Yeah.
basically what happens here is, so the computer is going to learn from the different features that's going to see in your data. So when you have when you have the target region, let's
Mhm.
say in this case cracks,
Yep. That yellow.
as a good example. So when you have the piece which is associated with the crack, or the pixels associated with the crack, or defined as cracks,
Mhm.
when that is basically the ratio is 1 over 1,000. So one is for
Yeah.
the pixel and 1,000 for everything else. When you have that, we call you have an imbalanced data set, and your
Mhm.
model, your mathematical model, your deep learning neural network, whatever you want to call it, should account for that, because you're not seeing so many of the crack pixels. You're seeing actually a lot of background. So what's going to happen if you don't count for that? Going back to the previous slide, which is the accuracy, if you do account for this kind of imbalanced nature of your data set, what's going to have is what you're seeing on the lower half of the slides is you're going to have false positives and the
Yeah.
false negatives.
Yeah.
Especially the false positives, it's gonna be a lot of that. And again, the last thing you want is, now you're trying to solve a problem, which is, let me give me the data, let me run the analysis, give you what kind of damages that you have.
Mhm.
The last thing is to add to on top of that and say, hey engineer, I solved that part, but now you have to go through each and every single image and make sure there's no false positive or false negative.
Right. Right.
So that doesn't make any sense. That's like defeating purpose. So when you're designing the technology, developing the technology, you have to take all of this into account.
Yeah, it's only something that this is going to take care of it for you, but then you also have to double check all of its work. That's a tough sell. So it has to be, there's always going to be a human in the loop. There's always going to be someone in front of a computer screen doing some clicking. But how much of that is going to be left to the human? That's the X factor, right? So
Yep.
putting all of this together and the AI that you guys have specifically built at AREN, this is an example you shared with me of corrosion. So you
Yep.
pick out a lot of different damage types, and you've built these models based on the material. So you showed me corrosion, and it looks black on the background, but what you've done here is you've adjusted the textures, so you were only seeing the corrosion. If
Yep.
you want to pull up the RGB textures and look at that, this is still a photogrammetric model. We have the lovely fact of having both images and structure and textures and mesh. So we can measure from it. You can calculate area, surface area, volumes, etc. All that is intact, and the beauty of it is that it's delivered in such a simple format and with all of those things in place to make it accurate and reliable. Here's an example that I collected. I collected this with the Skydio S2. It's by far the best drone to collect bridge data from, in my opinion. And I never collected it with this use case in mind, right? I was just there. We were doing a video inspection, which is typically how we've done bridge inspections. We had some extra time because we were done so fast, and we collected this data so I could test out some photogrammetry because I love photogrammetry. But one of the things that you detected right off of the bat, it's concrete. So you checked for efflorescence, cracks, and spalls. And I was really impressed. And anyone that sees this immediately understands what they're looking at, and they immediately understand where they're looking at, right? There's
Yep.
no
It is
ambiguity there.
contextualized.
It's contextualized, right? So that allows engineers and experts to really identify issues from a very high level, but also very specific as well, element to element, and something that may be not so important if it's isolated, but if there are other sort of things around it going wrong, then that's a big red flag, and that's again, you need to
And,
have the expert
and
look at
just
it.
to emphasize why it's important that you have these, labeled 3D models. So all
Hmm.
those damages, they're in different formats. You have the RGB model, and you have the hotspots for that fluorescence here, or the
Hmm.
one before, which was everything dark. Only the corrosion was available in 3D to see.
Hmm.
So there's two things which is very important. So number one is, now I've had many conversations with engineers that, they have seen drones, they have seen
Yeah.
3D models, but basically the impression was, it's cool, it's nice, it's a nice 3D representation of my asset. Yes, of course I can do some virtual inspection type of work on it. I can make
Hmm.
some dimensions. Like,
Yep.
that's all good, that's all benefit. But again, if I have to look at the 3D model, and now I have to spend hours and hours now this time on my computer to render the model and look for different damages and then annotate them
Yeah.
manually,
Yeah.
again, it's sort of like you're almost back to the same place of subjectiveness, inconsistency, and on top of that, having this tedious
Yeah.
task to do.
We got a comment here from Rotor Dynamics Corp. Selling drone inspection to engineering companies can be a challenging task, especially when those companies are still relying on software from the late 80s. That's it.
Yep.
You can't create 3D models and then send it over to them and expect
No.
them to even be able to open it, right? So
Yep. Absolutely.
um, I've experienced that myself, and this is something that you've thought about, of course, because you've heard it from the end users, and you've built around that
Yep.
constraint and that
And
problem.
that's why we are doing all the modeling in house, and then even
Yeah.
like through our platform, we can very easily render these models on different devices with different compute powers.
Right.
And that brings us to the second point that I wanted to make.
Mhm.
That is the quantification. By
Yeah.
having everything in 3D, now you can even quantify in
Of
3D
course.
and understand, again, the size of different damages, the depth of the spallings, and all that kind of stuff. And
Mhm.
as you mentioned, we do all of that per material. So we have, right now, right here, right now,
Mhm.
in terms of offering to our clients, we are working with clients on concrete assets, on steel, asphalt, masonry, stone, limestone, for example, and terracotta.
Yeah.
And it's important to mention, like, why we did it this way, why we did material based, because now we have this huge catalog of AI models for concrete,
Mhm.
and now we can apply that to a bridge like the one that we're seeing on the screen, Or we can apply the same model to cooling towers, to industrial chimneys, to dams, to levees, and you
Right.
name it. Same thing with steel, same thing with asphalt. So it just helps us to get to different verticals without customizing the technology, or tweaking different pieces of the technology.
Yeah. And so we had a question here. Is the solution already marketed in France or Europe? I haven't seen it yet. Well, it doesn't matter where you are because as long as you're giving it data that that is going to be able to work, right? Good data,
Yep.
then it works. So it's completely agnostic of the input source and how you collected that, as long as you did a good job. And of course,
Absolutely. So, and at the end of the day, we're a SaaS product.
yeah,
So, right now, for us, the way that we talk about ourselves is, if you have the data coming from, Paris, or coming from San Francisco, it doesn't matter to us, as long as especially it's good data.
yeah,
And regarding, like, are we working in Europe? Yes, we're working in US, in Canada, in Europe, in different countries, all the way to Japan. So
nice.
we are available
Yeah.
to get different jobs in different parts of the world.
And you're seeing all kinds of data. So one type of data that I've recently had a chance to run through AREN, and I'll take you guys through a little case study of first how we did the data collection, because that's, in my opinion, where it all starts. And at the end of this, I'll also share a link that Ali provided, and you guys can open the data set yourself. You can explore in 3D. And this just shows you don't need a device, you don't need a fancy computer to open this. This is a 2 kilometer runway, very high resolution. You can open it on your phone with a QR code. So check out this airport. We have an intersecting runway, and we're doing an asphalt condition assessment. And the interesting thing was that drones at airports are complicated. Everybody knows that, but it's doable. And we were really out there to discover how complicated is it? Is it scalable? And what are the things that people should look out for? This was done through an academic institution, and we had a little small opportunity of time where they were repaving the intersection right here. This runway was completely repaved at that point, but they left the intersection for last. So the airport was open. There were aircraft, jets, 737s going in and out throughout the day. It was a towered airport, it's an international airport. We have flights to all over North America from here, and we had to keep all of that in mind. We couldn't shut down the airport for this. Because there wouldn't be any point. We could just do it the traditional way, which is literally just driving down the runway and looking out the windshield. Call that a windshield survey. So, and that type of survey completely unquantified, right? Just random samples. The engineer, or in most cases, it's the airport operations people, are just kind of giving themselves a qualitative look at the site, and they're sampling different sections. So, our thesis was, let's see how quickly we can do this. Speed is super important, and we can't shut down the airport. Of course, we're going to be able to shut down that surface. That runway is not going to be taking takeoffs and landings, but you have to do that anyways. You have to do that if you're driving on it with a car, or if you're walking on it. Any human is on that airport surface. It has to be no-tammed and closed, and almost any international airport, larger airport with a tower. So a few of the things that we encountered that were interesting was, we were at an intersecting runway, so we had planes that were landing and taking off right above us. So we had to change the altitude at some areas. So this intersecting area, we had to fly lower to the ground, and then we kept the same altitude in the other sections. We had a tower, which was helpful, of course, but they have a lot to think about. They're servicing the aircraft, the manned aviation. They can't provide services to us. It's up to us to maintain our right of way. And then additionally, we found some interesting interference from the radome. So this is a very powerful radar. It's this big white sphere, and of course, it's emitting a lot of energy. You can't even be too close to it for long periods of time. And when we were flying, we noticed that the signal strength between the drone and us was degraded quite a bit. So this is for people that are thinking about doing this, maybe exploring it. Keep in mind all of these things that we learned, and hopefully you're prepared for them too. So we had a bit of a balancing act to do. We needed high resolution, high accuracy data, but we had a large area and little time to do it. We estimated that the data collection, it needed to be wrapped up within about 2 hours, end to end, and that's because we didn't want conditions to change. Weather is highly variable, and then also the traffic. We didn't want to disturb any of the airport traffic or cause any more problems, because they're never going to let us do this again. So high resolution means low GSD. We were using a 45 megapixel camera, a P1 on an M300. So that's very accessible. That's a workhorse in the industry. It's not super expensive. It's affordable. You can get it. Most people that do operations already have it. 45 megapixels is not that many. We had to fly low to support this mission. So that means low GSD, low ground sampling distance. So we were able to achieve a ground sampling distance of about 3 millimeters. And it turns out that the tower, after we did this flight, they actually preferred us to fly low. When we were flying at 100 feet, that was low for us. But they said, could you go lower next time? We could, and the reason for that was that when we were 100 feet, they could see us, and this drone was moving back and forth, and it was kind of confused. It was something that they didn't want to have in their sight and sort of think about because they're so busy. So that was the first thing that we learned. Low is good, so that's promising. But what happens when you get low is your speed is significantly reduced. So now you have all of this area to cover, and you have a little time to do it, but you're restricting yourself in flight speed because the camera can only take so many pictures. It generally, the P1 I think is advertised at about zero point 0.7 seconds, and as soon as you start dropping that altitude, that number has to climb because it can't keep up with what it's seeing below it. So we reduce speed. The way to overcome that speed reduction is to reduce overlap. So that brought speed back up. Generally, we collect this data at like 75 overlap front and side, and we reduced this to about 60 and 65 for side. So that got us back into that speed of things, and we were able to complete the data collection in that 2 hour window that we blocked. We got the data that we needed at 3 millimeters GSD. So every pixel represents 3 millimeters. It was a beautiful day, no wind, excellent imagery, really great camera as well. But when we went back and processed it, and this was actually before I had even met you, I tried processing this on a few different photogrammetry engines, which everybody knows I love to do. And I had some interesting problems. I had GCPs, I had 36 of them. We set them up as you're supposed to set them up when you're doing corridor mapping. We had PPK. We fixed the metadata in the image with PPK tags. So the position of the drone when it was taking that picture was very accurate. And all of this together in any other situation would have meant that it's going to be just a perfect, highly accurate map first time you try it. Well, this is what I got first time I try it. So people that are familiar with photogrammetry, this is in Pix4D Mapper, which is one of my absolute favorite applications. I love it, but it didn't do so well with this. And I discovered after a lot of tinkering around that this was related to the camera calibration. So because we had overlap that was less than typical, and we were flying close to the ground. And the runway it had a lot of features, but the features were very similar because it's asphalt here, asphalt there. The internal camera calibration did not optimize those values as it should. So I eventually fixed this problem. I got to the bottom of it. I made a post on LinkedIn about it as well, and I'll probably do a little bit more. But it was time consuming. So processing took a long time, about 24 hours, and I'm doing it on a fairly beefy computer. And I got my resolution. I was able to figure out exactly what that resolution is because of those ground controls. And overall, the model was within 1.5 centimeters in RMSE error, right? So the accuracy, even across the Z axis, the up and down, was within that 1.5 range. That brings up the question. I did GCPs, I did PPK. Did it matter? I ran this test 2 times, once with just PPK images and once with GCPs and PPK tagged images. And I found that when I processed it through AREN, the difference in length between the control point A and control point B that were the farthest away from each other horizontally was just 0.019%. That's zero point 0.3, that was 0.35 meters or 35 centimeters across almost 2 kilometers of distance. That blew me away. Doing control points in this kind of situation basically doubles or triples your time. We had to get out there at like 5 a.m. and start collecting these images. And turns out you don't need to do that. So this is a very efficient, very practical, and I think airports should be doing this. The amount of data that we collected was incredible. Shout out to the other photogrammetry engines that also had no issues, but they didn't have anything for the analysis. So I mean, I can't go and label 2 kilometers worth of cracks. And when we ran it through AREN, we had almost 16,000 cracks detected. And if you stretch those cracks end to end, every little branch, every little corner, it adds up to about 24 kilometers of cracks. And if you look at it, very, very, very few false positives. I was barely able to find even one across the entire data set, and very few false negatives given the data that I was able to provide it. So you shared this with me. This
Yeah,
is a peek inside the black box, right? AI is complicated, but can you explain what we're looking at a little bit here?
absolutely. So I put this slide together for a reason, and the reason is, you know, I've heard this many times that people are like, oh, like deep learning, it's a black box. Nobody knows what's happening there. Like I'm like, what are you even talking about? This is like a human being designed this, so of course we know what's going on there. So this is just a sneak peek of how the computer sees things and learns from them. So
Right.
in the first image, basically the image number one, as you have them here. So that's the input. So that's the
Yeah.
first thing that you basically want to run your inference, as we call it.
Hmm.
So then you have these deep neural networks that at each point it's running, different processes and like which we don't need to get to it, but essentially what it does is it extracts different features. So here you're seeing that the model is like getting, let's say cropping the
Hmm.
image smaller and smaller and smaller and learns from every single crack here, for example. So
Hmm.
as you're seeing here, it gets like super close up to the cracks. And even in those feature maps, you're seeing that the features on the cracks are different from everything else. So for example, that
Yeah.
the last one, the number 6, is a good example that the features are different, and those are the features that a computer learns, and later on it can make predictions moving forward. So this is just a sneak peek into the, as we
Yeah.
call it here, black box. This is what happens. So you have the input image, it goes through different layers, and each layer is learning something, and based on the things that it learns before, it's trying to assign a classification per pixel, and then you get the mask, and then you map that into your image. So now you have this very clean, semantically labeled model or
Yeah.
image.
So Lucas here asks, how accurate are your measurements based on the calculated GSD, right? So that is what kind of sets your smallest unit of measurement is your GSD. So we
Yeah.
collected at 3 millimeters. So I know that each pixel on that image, even after it's been processed by the AI, represents 3 millimeters on the ground. So it really depends is my answer. And I think you put these slides together to kind of show how that measurement is being taken and how
Yeah.
often it's being taken, right?
So this is again another sneak peek of why you have to go through all of this to do semantic segmentation, 2D and 3D, because again, remember, at the end of the day, you want to provide quantification.
Hmm.
Cracks, you want to know the width of them at each point. Spallings, you need the diameter and the depth, and so on and so forth. So this is just showing, for example, now you have the images on the left hand side. On the top, you see the mask, which everything in black means the background, and
Yep.
white is showing the cracks, or the everything that classified as cracks. And then you're seeing that at each point within the length of that crack, we are calculating the width of that crack. So
Hmm.
when we are providing the reports to the clients, so we do that per crack, and we provide, for example, different stats about them. So it
Yep.
can be like the mean width and mean and max width and all that kind of good stuff. But
Right.
essentially, in order to do that, you need to do it over the length. So here you're seeing a heat map, or the crack map, with a heat map for the entirety of that 2 kilometer runway.
Yep.
And at each point within the length of the crack, you have the quantification information. So as you're seeing here in the legend here, everything which is with a greenish color, it's less than 6 millimeters.
Yep.
And then you go up until like the red colors that's showing actually bigger portions or bigger cracks or bigger width along the length.
Yep.
So again, you
It's
have to do all of that in order to do the quantification.
exactly, and this the equivalent in the real world, or the current standards, I guess, if there's no standards for this because it's so in depth. But what you would have to do to replicate this would be basically to get out your crack gauge or a ruler and then measure the
To
width
show it
that
to the
the
audience,
yeah,
that
that
is the
thing,
crack issue we're talking about.
and measure it every 3 millimeters down the crack for 15.5 kilometers worth of cracks. No, that's never going to happen, right? So, if anything, this is orders of magnitude more data than we're used to, but it's data that matters because, as any engineer will tell you, it's the crack width that they care about, not so much the crack length. And seeing the relationship between the crack length, the crack pattern, longitudinal, transverse, alligator cracking, what's happening in terms of just how they're arranged, gives you a lot of insight about what the potential issue would be underneath the ground, right? So then you can maybe go and ground truth it. You can go and do a GPR, a ground penetrating radar. You have a starting point because you have all of the contextual information and all the quantity information together. So this is available for the audience to check out. So AREN uses the Nira viewer, which everyone knows I'm also a huge fan of. But the big X factor there is that all you need to open it is a device that can play video, and you'll be able to open a 3D model. So on your screen is a QR code. If you pull out your camera app and look at it with the camera, you don't even have to take a picture. You can open up the link and you can take a look at the model itself. So dive into that. And if anybody has any questions, I'll go through some of the comments that were made, and then Ali, you can answer them. All right. Uh, so I think we've answered this one before. Does ARN host the models, and does the annotation give a severity scale?
Yes, yes, and yes. So yes,
Yes. Yes.
it's all the it's proprietary models that we've generated in order to serve our clients, and yes, you're hosting everything there.
Perfect. Next question: is it possible to use a national classification system? Germany has different systems for
A-
damages than the U.S.
Absolutely, absolutely. So the way that I always look at this is like the most difficult part is the quantification,
Hmm.
which is like now you have all the information. How you are putting the severity class and assign that to each of them, it's correct. It can be different in different countries,
Yep.
and that's, let's say, it's the easier side of things. And because, as I mentioned, because we're working in different countries, we are very much used to this, so we can easily adopt to whatever standard that you have in that particular country, or even for that particular asset. So
Yep.
sometimes, the asset owner, they want to have even more granular information than what the standards of the country tells them to do.
It's just pixels on a screen, right? And that leads to the next question: is can we rely on ortho photos? And in this case, I'm pretty like some of the files that you delivered to me, you included ortho photos in that, right? So an ortho photo is a 3D model basically flattened from a perspective. So you can do both, right?
Yep.
Is there anything that I'm missing there?
No, you can do both. And then, in fact, when you're looking at the deliverables, we provide both of them. So in a case of a flat surface like this one, it's going to be just one orthomosaic, which is covering the 2 kilometers. In terms of the bridges, it's going to be each face of the elements you're providing that orthomosaic, and we're reporting based on that one.
Mhm.
The reason we do that is, it's just easy copy paste into whatever PDF format that the engineers
Yeah.
have to report to the owner. So we are just providing all of that information to them.
Yeah, and PDF is still king, right? I always tell people in the 3D world that
It's
we're we're competing with 3D data, with 3D data versus PDFs at the end of the day.
little
Um,
by little will change it.
Next question: is it possible to detect crack depth? And I can answer that right off the bat. I tried doing this. If the crack is wide enough and the width of the crack is wider than the pixels, and in some cases maybe even just slightly, you can. It's GIS data, right? You pull it into something like QGIS, and you use the profile tool and draw a line across it, and you'll see the profile. And I was actually able to match visual cracks in the ortho to a significant dip in the Z height in the profile view. So it really just depends on your data. If crack depth is super important to you, then make sure you get data with the resolution that allows you to do that. Right? Am I wrong there? Have you seen this from your clients?
So we are giving the same exact answer. Like, you, if that's what you're going for, you have to pick a right camera at the right distance with the right focal length to get to a GSD number that provides that depth for you.
Hmm.
Um, that's the only way to do it. And with all of this, you have to remember. I mean, it's intuitive, but it's like if you're looking at 0.05 millimeter crack, I'm talking about within this particular case, you cannot expect to achieve that with a GoPro camera and you're standing like 100 meters away.
Yeah.
So you have to do better than that. So,
Yeah.
but yes, if the GST complies with what you're looking for, the depth is going to be is wide enough to see the depth, then we can actually detect it and quantify that.
Perfect. Next question. Sorry, the names aren't coming up, everybody. Hello, thanks for the explanation. Are the projects based on photogrammetry or combined with LiDAR point cloud capture? I've done combined merge data sets where we go and get LiDAR and we use that for the surface, for the mesh, and then throw the photogrammetry in there as well. And we get the best of both worlds. We get the accuracy and resistance to those materials that LiDAR provides, and we get the visual information from the pictures. So I've done that in a few different software applications that are running your desktop, like reality capture. But can AREN also support that if you are uploading that into the AREN pipeline?
Yes, yes, absolutely. So, and we have done that on
Love it.
several projects. For example, like inside of the box girders, that they had like laser scanner and they had images capturing the walls, and that's how we actually put together a fully detailed 3D model of the box girder. As
Hmm.
just an example. But yes, the short answer is yes. We are able to do that.
Excellent. Benjamin says a runway is bathed in ambient light. He's absolutely right. What constraints act on careful, useful data for poorly lit surfaces, dark underbelly of bridges, dynamic range issues, shooting into the sun? Oh boy, I could talk for a day straight on this topic. You have to collect the data as it is, right? So the camera matters, the exposure settings matter, the file type matters, right? JPEG versus RAW. I'll talk your ear off about why RAW is so important for me. If you can see it in the picture and if you can extract it from those pixels because the sensor was able to trap it, then you can get it into a pipeline like AREN and then do these detections. And as we talked about with the data augmentations, that's, I think, one of the most important parts that you have to get right. Those augmentations are there so that a variety of imagery will work, even dimly lit in some cases. If there's enough information there in the pixel level, it will work, right? So again, it always goes down to the data collection and the field work. It's a bit of an art and a science, but if you can do it, you can get results. And that's getting easier and easier thanks to technology, thanks to better cameras, to better drones, and everything like that, right? Alrighty, next question. Can we mix 3D photogrammetry models with AR? Interesting.
Right now, we don't provide the capability to do augmented reality on our platform.
Mhm.
But is that something doable? Yeah, absolutely.
Yeah. I mean, it's the same. It's just if you have the 3D data, you can put it into AR somehow, right?
Yeah,
You have to
like
do. There's a few
like a
steps.
platform like Sketchfab and all of that to provide that kind of functionality. So that shouldn't be difficult.
Yeah, yeah. And for visualization, that can make sense, especially if you're trying to show someone and have them see it in 3D, stereo vision like they're used to.
Yeah.
This is an interesting question. Can you conduct these scans at night with IR or pure LiDAR?
So again, the answer is going to be yes, but it's one of those cases that you really want to conduct these in pitch black type of scenario that you don't see
Mm,
anything. Like, uh, I don't think it's a good idea because,
mm,
why not using the artificial light to light up the scene, and then you can get even more information.
yeah.
So you're out there, you're doing the data collection. Why stick to these only pure lidar and IR? Why not doing the photogrammetry as well?
Yeah, and I'm not sure if by IR you mean like thermal, like shortwave infrared. And I've done a lot of research on specifically bridges and applying thermal sensors to them to see for damage. Sometimes it can work, but a lot of times it's kind of it's still not really a definite answer. I don't really think that it has a huge part in that type of structure, but it may be there. At the end of the day, though, IR, if it is thermal that he's talking about, or if it's another type of IR, if you can get the imagery and there's features that you can detect, you could train a model for it. So if there is a huge use case for it, then I'm sure that you guys would be on it because it's just data at the end of the day, right? It's just pixels.
Yep.
Yeah. Okay. Do you know how much this method can reduce monitoring costs and time compared to the traditional method?
Yeah, absolutely. So we have seen. So it depends. Like it's a range. So it goes from, I would say, 30% all the way to 75%. So 75% one, which you're doing the savings, it's going to be on the signature assets, on the humongous big assets that, let's say, it's kilometer long or kilometers long, and now you have to do the crack mapping. Traditionally, that takes a month, and
Mhm,
with this technology, now you can do it. Let's say less than a month. So the bigger the asset, the more complex it is,
mhm,
and the more heavily damaged it is, then you're going to see even more and more um, cost saving essentially. But the way that we also look at it is it's not everything about the inspection itself. It's more than that. So not only we are saving time on the inspection and all of that, we're saving time, we're saving money on the repairs. So and that can happen in two ways. Like not all the cracks need to get repaired. So by having all this information, now you're only repairing or cracks as an example. I'm saying you're only repairing the one that in dire need of attention. So
mhm.
that we can again save between 30 to 50% on that particular front. On top of that, when you're actually having a repair process going on, but now having the full view of the issues and the damages, now you're going to have less and less change orders as you're doing the repair. So again, it's going to be cost saving. So it's not just the inspection; it's the whole 9 yards, I would say.
Yeah, yeah, and it all goes together, but at the end of the day, if you can get to a problem before it becomes a big problem, the cost and time that it requires to use something like this to get that answer is insignificant compared to the money you're going to be saving when an event is triggered and you absolutely have to repair it, right?
Yeah.
These aren't cheap and easy assets to fix. Paving a runway, I think the figure was in like the tens of millions of dollars that we heard from the airport operations. So it's worth it every time because you can plan for that. And with previous methods, you can't really plan. It's a lot of intuition. It's a lot of sampling. There's a lot of luck involved. Of course, you can do more and more of it, but pretty soon you're gonna be spending more money doing it the traditional method then you're going to be doing it once with this and then repeating it occasionally. All right. Does Aaron have a trial version?
I mean, contact us and we'll talk about it. But
Yeah,
yeah,
that's what that's what
we're open
that's
to that.
that's what I did. I said, "Hey, Ali, I like your product. Can you run this runway data set?" And you're like, "Yep." And then in 3 days, you had the data back to me,
Yeah.
which blew my mind. And I'm always skeptical of AI, quote unquote. Um, but 3 days for this amount of data, there would have been no way to do that manually. So for sure you're doing something right. And yeah, the best way I think is to just reach out.
Yeah.
Mhm. Some questions about this. Are you going to be sending the recorded version? So this is being streamed on LinkedIn and on YouTube. Both of them retain a recorded version. If you RSVP to the event, you can watch it back. I know there's a lot of information. It's information dense. You might have to watch it twice, especially the beginning parts when we talk about the AI. But it's going to be available. So anytime, watch it back or reach out if you need another version, a file, or the presentation. I'm totally open to that. All right. So I hope people have had a chance to take a look at the model through the link on the screen. I'll probably be doing some follow up data. Ali, if people want to follow you, follow Aaron, what you guys are doing, what you're up to, how can they do that?
So, of course, they can find us at AREN.AI. That's our webpage, and through that they can contact us. My email address is also very easy, Ali at AREN.AI.
Whoa.
That's one of the privileges of being the co-founder of the company, I guess.
Yeah, and in
And
terms of the company, how big is the team? And you guys are fairly young, startup, but are you growing quickly?
yes, yes, we're growing quickly. Right now we are almost 10 people, and we are keep growing fast, and we are, as I said, we are working on big projects, some signature assets in North America, as well as P3 projects, for example, in other parts of the world, and we're keep growing, and we are keep taking different tasks. So we are opportunistic, especially if you're seeing something with legs and something that is scalable. Let's say it's a particular type of an asset, such as this airport runway, and we see that you can actually have a one hat fits all type of scenario. We are taking it, and we are open for all those conversations. So, as I mentioned, my personal email, ali at rn.ai, or through rn.ai, they can reach out. We're available, happy to discuss trials and even different projects that people are taking on, and to see how we can provide value to them and to their and clients.
Yeah, and it doesn't matter on the region of the world that you come from. If you bring your own data,
Yep.
and then RN will take care of the rest, and that's how I've been doing it with you guys. Um, One last question. This one was kind of interesting. Cracking of concrete, yielding of longitudinal steel and intention, blah blah blah. Lots of different damages here. I think that at the end of the day, everything has a place in terms of where it fits on the scale. If you have the data that sees that damage, then you should be able to pick it up or build a model around it.
Yeah.
So the question is, can you see this? Can you see that? Can you see that? You have to actually see it first, right? This is an X-ray vision. So if you have the data, it will be able to detect it. Am I right about that?
That is absolutely right. And on top of that, again, that's the part I always like to emphasize. We're augmenting the process. So you have the human in the loop, and that, let's say, is our client, the civil engineer. So we give all of this data to them, and then they're started to see, okay, now you have, I don't know, this kind of cracking here and that kind of cracking there, and like
Mhm.
these are the sizes of them, and maybe what goes wrong there, and maybe they have to go out again and do another test, some NDE methods. Like, this is all about making sure that the engineers have the right data to make decisions
Yeah.
of them. So it's not about, oh, we're going to replace the engineers with a machine. None of that going to happen. So it's all about helping them to to do the job easier and faster and more thorough.
Yeah, that's it. And engineers have they have a lot of work ahead of them. They've always had that. It's a tough job. It's hard to become an engineer. They have better things to do. They shouldn't be
Oh
poring
yeah.
over PDFs and drawing lines where the cracks are. So let's free them up. Let's give them some tools, and let's get our infrastructure and our assets in a better state for the long term through that. All right. So thanks everybody for coming. We're gonna wrap it up here. Reach out to Ali. Reach out to myself. Follow us on LinkedIn. We'll keep posting more examples as they come up and as we do some more projects together. Have a great rest of your day, everyone. Happy weekend soon. And that's it from me. Ali, anything else?
Yeah, thank you so much for attending. I hope you found this webinar exciting and interesting. Intentionally, we wanted to show a little bit, be more technical, and show a little bit more about the technology itself, other than just showing you 3D models and just close-up images with a box around the damage, which is, it is AI, but it's not useful for the engineer. So we wanted to just make it more exciting for everybody, and I hope we were successful on that front. So, as I mentioned, we can reach out to us over LinkedIn, and send us messages, send us emails. We are around, and we always love to talk about technology and what we're building.
Awesome. Yeah. And it sounds like people really did enjoy this. We'll probably do another one soon. So check back and bye for now.
Have a good one, everybody. Bye bye.